So we're going to have a look at a differential equation from 1981. So in this question, we're told that a particle moves in a straight line so that at any instant its acceleration, which we are going to call a, is equal to half its velocity. So equals a half of v. If its initial velocity is 3 meters per second, find an expression for the distance it describes in the 5th second. So we're interested in this question in finding out how far the particle travels in the 5th second. Now note that the distance travelled in the 5th second is a very different thing than the distance travelled in 5 seconds. So what we're interested in here is how far did it travel from the point in time when the time was 4 seconds to the point in time when the time was 5 seconds. And so that's the 5th second, the distance described in that 1 second. Now we know that if we have an acceleration is the change in the velocity over time, so dv dt, and so we can say that dv dt is equal to a half v. The problem with this differential equation is that this combines velocities and times, and we're interested in finding a distance, and we're going to call that distance s. So this formula on its own won't find a distance for us. The other formula that we can use is we can take dv dt and we can, using the chain rule, rewrite it as dv ds multiplied by ds dt. And remember that ds dt is the velocity. So ds dt is the change in the distance over time, and the change in distance over time is velocity. And so this formula can be written as v dv ds. So if the acceleration is a half v, we can say that v dv ds is equal to a half v. And this is our second differential equation. So we formed two differential equations, and both are going to be useful in terms of solving this question. So this second differential equation that combines velocities and distances can find displacements for us, or distances, s, but we're not going to sub times into this equation. What we're going to have to sub into this equation is velocities. What we're going to do is we're going to use the first differential equation to find the velocities, let's call it v1 and v2, after 4 seconds and 5 seconds, and then use those in the second differential equation to find the distance travelled, not in the 5th second, but the distance travelled in going from a velocity of v1 to a velocity of v2. And so that's the way that we're going to tackle this question. So we're going to start with a is equal to a half v. We're going to change a into dv dt. We are going to collect the v's on the left and the t's on the right. If I divide both sides by v, on the left I get 1 over v dv, and on the right I get a half dt. Before I integrate both sides, what are we trying to find here? Well, we're trying to find the velocity, let's call it v1, after 4 seconds, so when the time is 4. And we know that when the time was 0 at the very start of the question, that the velocity was 3. And so they're going to become our limits of integration. So we're going to integrate the left-hand side with respect to v, so 1 over v from 3 to v. And we're going to integrate the right-hand side with respect to t from 0 to 4. The integral of 1 over v is the natural log of v, and the integral of a half, which is just a constant, is going to be a half t. We're going to sub in our limits, v and 3 on the left hand side, to give us that the log of v minus the log of 3 is equal to, and subbing in 4 and 0 on the right hand side, a half by 4 minus a half by 0. We're going to use a rule of logs to combine the log of v minus the log of 3. So we know that the log of a minus the log of b is equal to the log of a over b. And so the log of v minus the log of 3 is equal to the log of v over 3. And that's equal to a half by 4, which is just 2. The natural log can also be written as the log to a base e. And so if we rearrange this equation, we get that v over 3 is equal to e to the power of 2. I'm going to multiply both sides by 3 to give me a velocity of 3e squared. I'm also interested in the speed the particle was moving after 5 seconds, so let's call that v2. And again, I know that initially, when the time was 0, the velocity was 3. So it's the same differential equation. All I'm going to do is I'm going to change the limits, and more specifically I'm only going to change the 4 into a 5, and so I can actually start from this point of the equation rather than actually going back and reintegrating the sum again. And so this time, subbing in a limit of 5 we have a very similar sum. We have the log of v minus the log of 3 is equal to a half by 5 minus a half by 0. Again, the log of v minus the log of 3 is the log of v over 3. That's equal to 2.5. And then we have that v over 3 is equal to e to the power of 2.5. Multiply both sides by 3, and we get v is equal to 3e to the 2.5. Now that was the velocity of the object after 5 seconds, 3e to the 2.5. So as mentioned before, we're not going to find the distance traveled in a particular time. Rather, we're going to find the distance traveled from moving it with a speed of 3e to the power of 2 to a speed of 3e to the power of 2.5. The reason we're doing that is because we have a second differential equation that says that a is equal to half v, and a then is v dv ds. So if we know the velocities, we can then find the distance traveled in moving from one velocity to another. Whereas we don't have a formula that combines t's, the time, with s, the distance. So this time I'm going to divide both sides by v to give me dv is equal to a half ds. I'm going to integrate both sides. So I'm interested in how far did the object travel in the 5th second, which is the same as saying how far did the object travel in going from a speed of 3e to the power 2 to 3e to the power 2.5. So we're going to start measuring the distance when the time was 4 seconds, which was when the velocity was 3e squared. At that time, the displacement obviously is 0. And then we're interested in how far it traveled until t equals 5, when the velocity was 3e to the power 2.5. And we're going to call that displacement s, and that's what we're trying to solve in the question. So if I integrate the left-hand side, so the integral of dv is just v, and then on the right-hand side, the integral of a half is a half s. I'm going to sub in the limits, so on the left I have 3e to the 2.5 minus 3e squared, and that's equal to a half s, minus a half times 0, but a half times 0 is just 0. I'm going to multiply both sides by 2 to give me a displacement of 6e to the 2.5 minus 6e squared. And if I throw that into the calculator, we can say that the distance traveled in the 5th second was 28.76 meters.